Hello and welcome back to Calculus 3 for one last time. This is the final lecture of our Calculus 3 course, and this will be featured tomorrow on the final, so pay attention, right? The Greens Theorem is one of those quality of life kind of sections. If you are willing to work on line integrals, then you actually don't have to learn this ever, right? But this method, when the conditions are met, turns your very long and painful line integral calculation into two-line double integral calculation, which is over either general region or rectangular region, or maybe even polar, whatever you have. So technically, this section is there to, or the theorem is there to make a joke out of certain line integrals, so you don't have to spend eternity solving those. We are going to have two forms for Greens theorem. One form will be circulation form, and the other one is the flux form. So let's take a look at the definition, and then the example, and then definition, example, and call it a day. So circulation form. So for the circulation form, we have, let C be a simple, closed, piecewise smooth curve, piecewise smooth curve, oriented counterclockwise, that encloses a connected and simply connected region R in a plane. It's a whole shopping list of things that need to be there. That encloses a connected and simply connected. Region R in the plane. Assume F is a vector field where F and G have continuous first partial derivatives. Then, and now we have this integral sign with a circle around it. Now, this circle, guys, just means everything that I underline over here in blue. So the line is smooth, oriented, encloses the region that is connected and simple connected. So all of that good stuff. FDR, this is the standard notation for our line integral. Standard again, we did this last class. And here is the new stuff. It's the same as the double integral over the region R, and now you have the g dx minus the f dy dA. technically it's telling you that the line integral equals the area in the region. Now, before you freak out, line integral equals the region, 1D equals 2D. No, no, no. We know that the line integrals compute area of the curtain, right? So there's that. And then you have a double integral on the other side, dA, so they match. Good. So this is the circulation form. We are going to do the example of the circulation form. The partial derivative you see is called the curl. So this over here is defined as a curl of f. Curl of the vector field. So curl f is given by the partial derivative if the curl is 0, we say that the vector field is irrotational, doesn't spin. So this is what we have for as a Greens theorem for the circulation part. So we can take a look at the. So let's take a look at the circulation, right? Using the rotation field. You remember that we had to do a lot of mathematical gymnastics, right, on the unit circle over there to calculate the circulation using the line integral. Now with Greens theorem. It's going to be a joke, nothing. Let's see. So we have our vector field as a negative yx. This is our rotational field, and we are going to be on the unit circle. Clearly, unit circle is it's a smooth curve that it's differentiable everywhere, doesn't have any sharp edges, it's a circle, right? It's oriented because it's oriented counterclockwise. We know that through parametrization r, well, in this case 1. So cosine theta comma sine theta. So it's oriented counterclockwise, it's piecewise, it's smooth, it's all of the good things that are necessary. It's closed, right? So it's a closed line, and it also closes in a region, right? So which has no holes. That's the simply connected part in the definition. So everything, all of the conditions from the theorem are satisfied because the unit circle matched everything that we have. Guys, squares, rectangles, triangles, they're all gonna do this. Half of the circle that is connected with the line on the bottom is going to have all of these, except you have to calculate them piece by piece. So now that we have this problem, I am going to say that we can calculate the curl, and once we calculate the curl, we plug that into the integral, and we are done. So first we calculate the curl of f, right? Our vector field. Curl of f would be the partial derivatives. So I have the g dx is going to be 1, and then a minus, and then the f dy is going to be negative 1. So curl of f is 2. Now our unit circle, right? Our unit circle is nicely set up for polar coordinates. So I will say that our integral f dr, f dot dr, is going to be the double integral of the curl, which is 2, and now I'm going to do this in polar coordinates, so r dr d theta, because it's a circle, so why mess with the trig substitution if I can just do this simply. Radius is from 0 to 1 and 0 to 2 pi on our things. So now when you look at this, it's a joke, right? Computing this, remember how many hoops we had to jump through to get parametrization, then get the speed, then plug everything in, right? It was a lot of calculations to get the line integral. As you can see, this is 2 steps, right? When I integrate 2r, I get r squared, so 0 to 2 pi, r squared from 0 to 1 d theta. Well, that's just integral 0 to 2 pi of d theta, which is 2 pi. It's a single line calculation. To get the same 2 pi, we got, let me switch back to line integrals, circulation. This was the circulation definition for line integrals, and then here is the rotational calculation, right? So we had to play the game of jumping into figuring out all of these guys, and then got the 2 pi at the end, which we now have with pretty much 0 effort. Now clearly, Greens theorem doesn't work for every problem. It works only for the problems that have oriented curves that are oriented and smooth and closes off the region, right? There are no holes. It's a single region and all of that kind of stuff. So everything has to hold in order for this. If the curl is 0, you will be integrating 0, right? And then obviously for circulation, you are getting 0. We call those irrotational vector fields. So you have a rotational magnetic field to create electrical motor, right? And you do not have a rotational magnetic field in a transformer, right? You are switching the polarity in a transformer to induct electricity. So electrical field creates current through the size. So if you want to go from 110 volts, which is in the outlet, well, 118, that is in the outlet, down to 12 point something for your cell phone charger, or 5 point something for your cell phone charger, right? That's not a rotational magnetic field, right? But you have to have this component. It's designed by Tesla. Not Tesla, Nikola Tesla, 150 years ago. So that's that. And now we have the flux form of the Greens theorem, which will use divergence to compute the... so flux form. Same conditions. Conditions apply, right? And then we have that the flux form, right? We use the normal vector with the so this is the outward flux. I asked you to think of a fan that has the surface area pushing the vector field called the wind perpendicular to the surface of the fan. Flux is how much stuff is coming out of the area. If you have the end of the hose, how much water is pushing perpendicular to the flat cut of the hose, right? So that's what the flux is, just how much stuff is propelled. It's called the outward flux. It is going in the direction of the normal vector to the surface from which the stuff is radiated. So at each point on a surface of the sun, for instance, you have the UV radiation go perpendicular to the surface, to the tangent plane at each single point, which is actually just going directly from the center of the sun to the point that particular ray goes like that. So that's what we have. It is going to be now the integral on divergence. So we have f dy minus g dx, and we have the divergence. So again, we have the region R for the double integral, which could be rectangular, general, or polar. And we have our good old partial f, partial x, plus partial g, partial y for dA. And we call this two-dimensional divergence. So the way this is defined is that divergence of vector field F is equal to partial f, partial x, plus partial g, partial y. And then if divergence F is equal to 0, we say that the region is source free, meaning there is nothing to radiate stuff out. Fan is off, all right? It's not spinning, it's not pushing the air forward, the water is not turned on. Guys, when you shut off the water in a hose, the garden hose, the water is still in the hose, right? It doesn't empty, right? The water is still in the hose. The same thing when you interrupt the circuit, the electric potential is on the both ends of the switch. So when you close the circuit, it's instant electricity. When you open the hose, if you didn't empty the hose, right, after the use, which means you disconnect on the other end and then you somehow get all the water out, right? So if you water your plants or chili peppers, whatever, and then the next day you come in, you open the water immediately goes out, right? So that's that actually. It's so simple, right? You won't find that in the gardening section at your local Lowe's store, right? But it is what it is. So we have the divergence now, and if the divergence is 0, that means that there is no source that will be giving off radiation, water, wind, or whatever vector field you are observing. Now we are going to have the calculation for our radial field, and we should get 2 pi using Greens theorem. So radial field on the unit circle should give us 2 pi, because we know that answer from our 14.2 lecture. So our radial vector field F is given as xy, and our curve C is the unit circle. Now again, I have been asked in the past, how do you know which formula to use? Well, I know what I'm calculating. Am I calculating flux or am I calculating circulation? That's the formula you use. But when you see a problem and it doesn't say, well, then just skip the problem, right? Because the problem is not clear, right? Generally, when you are working on the applied problems, you pretty much have an idea of what you're supposed to find, right? If you're designing a jet engine, well, it's how much air you can push through it so you have propulsion, right? It's flux. All right, so now we have the we have this, and then I'm going to well, I can draw the unit circle on the side, say it's 1, so we know that much. And then I have the divergence. So we calculate the divergence of the field. So divergence of the vector field will be 1 plus 1, which is 2. And now we set up our double integral, We are going to use polar coordinates again, r, d theta, because it's a unit circle. It can be done over a square and triangle and whatever, as long as the region is closed. Please remind me to talk about sharp edges on on squares and triangles and things. Because where's the smooth, right part? We have this, and then I have r is 0 to 1, and then this is 0 to 2 pi for the full circle, which would equal to 3 dots over here equals to 2 pi, because we already know what happens. And as you can see, this calculation is a joke in comparison to what we did for line integral. So guys, Greens theorem is a quality of life kind of calculation. It is not something that is fundamental mathematical thing that if we take Greens theorem out, is just mathematics falls apart. It is a very convenient way to compute when you have line C to be closed. You cannot use Greens theorem if you just have a line segment from 0, 0 to 5, 5. No, you are stuck with the line integral that we did in 14.2. But if the line is closed, then, and if it follows all of the 5,000 conditions, right, that are there, then you can use Greens theorem and greatly reduce your calculations. Now, the part that the function, the curve C needs to be smooth, and then I said, yeah, this works for a square and a triangle, right? You have to be very careful when you read this, because it says piecewise smooth. Not smooth, but piecewise smooth. Now, piecewise means that you get to cut it, right? And now if those portions, when you cut it, end up, joining into a square or a triangle or some kind of corner, that's fine, all right? The pieces of it need to be smooth. So that means that I could have 3 linear lines that connect the sharp edges, right, and the calculation will still work. You will be setting up the triangle double integral, right, the triangle, and then you would work. So you're technically, this section is converting. This section is converting the line integral into a double integral from chapter 13, and you just calculate that double integral. So the theorem is just, as I said, quality of life, right? Improvement on calculation, and that's that. We also defined, be very careful with the wording for those, the two-dimensional curl and divergence. The exam question could be just calculate the curl and divergence, right, for something. So you just calculate the 2 partial derivatives. Also, pay attention which way these guys are laid out. So you have your curl as dg dx minus, and then divergence is df dx plus. So be careful. Make sure you memorize these formulas the way they are presented. That's it. I hope you're not disappointed. Tomorrow is the right. You get to show off your math skills tomorrow. So bye.